Hi, I'm Mr. Franklin, and in this video, we're going to basically take all the pieces that we've been talking about individually. We're going to take our distance versus time, velocity versus time, acceleration versus time, and net force, and we're going to put all this information together, hopefully to give you a big picture of how all the pieces fit. So we're going to take a soccer ball, and we're going to run a timer for 4 seconds. So the soccer ball sitting here on the ground, and we're going to click the timer. Ready, set, go. There's 1 second. And there's another second. And there's another second. And there's another second. So our dots are not moving. So we could say that this one is at rest. So the ball is not moving. So if I were to graph this, I started at time equals 0, and for 4 seconds, I didn't go anywhere, okay? So that distance is 0. If I take the slope of that graph, we've learned that that gives us the velocity. Well, what's the slope of a flat line? Well, it's another flat line. So at time equals 1, the slope is 0. At time equals 4, the slope is 0. So the entire slope is 0, and we graph that, and we get a constant speed of 0. And if we continue, we can also take the slope of this graph, and it gives us the acceleration. And if we graph the acceleration, it's the same thing. It is 0. So I like to do hand motions with this. If I have a flat line to start with, it's flat, 0 slope, then the next graph is going to be flat at 0, and then the next graph is going to be flat at 0. We can move it over, and as long as it's at rest, we would get this. It's at rest, but it's not at the origin. But the slope would still be 0, and which means the acceleration must still be 0. Flat distance graph gives us 0 velocity, which gives us 0 acceleration. What does this mean? So if we have a 0 acceleration, then the net force must be 0. And the real basic way to think of it is if F equals mass times acceleration, if acceleration is 0, 0 multiplied times anything, doesn't matter what the number is, the force is going to be 0. So that's one way to think of it. Another way to think of it is this way. If I were to draw the forces acting on this soccer ball, we have the force of gravity pushing down on the ball and the ground pushing back up. And if I were to take the net force, which is adding both of those together, one is positive and one is negative, and they're the same magnitude, they have the same value, they would cancel each other out and the force would be 0. It's amazing. Physics works. So if the net force is 0, we often say that Newton's first law applies. Well, it always applies, but this is a great example of Newton's first law in action. This time we have constant speed with forward motion. So this time our soccer ball is moving on, we'll say it's moving on ice. But when we start the camera to track where this ball is, it's already in motion. There's no kick, there's no forces, it's just rolling across the ice. There's no force slowing it down, it's just rolling across the ice. So if we were to look at that with our little camera, we start at time equals 0, it's at the starting point, and then 1 second later, it's going 2 meters every second, so it has traveled 2 meters, and that's in 1 second. And then it goes on to another second and another second for a total of 4 seconds. If you add all that up and we graph this, then my distance is actually going to be 8 meters. So if I graph this, I would graph it like this. We started at the origin, and in 4 seconds, we make it to 8 meters. I didn't speed up, I didn't slow down. Well, now this is a straight line. It has a constant, unchanging slope. So the distance is changing, so there is a slope, but the line itself is straight. It's not a curved line. So once again, we are going to take the slope, and we could do that rise over run. So we're going to have 8 divided by 4, which is 2, which is what I said over here earlier, 2 meters per second. Well, if I graph y equals 2, I'm going to get a flat line, and that's going to be 2. velocity is 2 meters. Everywhere in that 4 seconds. So right here it was 2 meters per second. Right here it was 2 meters per second. So everywhere on this graph, the velocity is unchanging. So if the velocity is unchanging, that means zero slope. So if I take the slope of it, my acceleration is still 0. So we started up here with the distance graph, and we watched the soccer ball travel a distance of 8 meters over 4 seconds. We looked at its change in its distance over time, which is called slope. It's also the definition of velocity. Then we came up with 2 meters per second. So now we have an angled straight line, hand motions here. We have an angled straight line, which results in a flat line for the next graph, which a flat line then results in a 0 slope, okay? So far we've got distance is unchanging, it's at rest, so velocity is 0, acceleration is 0. We've got distance at a constant forward motion. Velocity is unchanging at a constant value, and the acceleration is 0. So increasing, constant, 0. And then we've got the other one at rest. Constant, 0, 0. Okay, let's take a look at the forces involved. So I said earlier, if the acceleration is 0, then the net force must be 0. I don't have to do any calculation. If I know that the acceleration is 0, the net force must be 0. But let's take a look at what these net forces might be. It's the same net force. We're assuming that there's no friction and that we didn't see any kind of push or kick from the soccer ball, okay? And this is hard to understand sometimes because in our actual experience, there are other forces. Somebody did kick the ball. There was friction, okay? But if you had looked away when somebody kicked and then turned the camera on late as the ball was already rolling, you would get some constant speed out of it. There was no friction. Okay. So Newton's first law is at work here. It always applies, but it's at work. We can see it because the net force is 0. The motion remains unchanged. The velocity remains unchanged. It's constant. So in the previous one, the velocity was constant at 0. And in this one, it's constant at 2 meters per second. So if velocity is constant and your acceleration is 0, then Newton's first law is at work. Okay, in this example, we're going to be doing constant speed still, but backward motion. So in this case, the ball is going to be going this way. So we still are defining our starting line as right here. This is our reference point, is the fancy physics word for it. And as the ball is rolling towards the reference point, we're going backwards from what we generally consider positive. Because generally we consider to the right positive, and we consider up positive, just like if you were looking at a graph. And negative would be down, or to the left would be negative motion. Okay, so we're moving in a negative direction, but we're starting away from the origin. So we're starting away from the reference point, and we're going to move towards the origin at a constant rate. So we're going at a constant speed, and we're going back towards the origin. Okay, now notice this one has a negative slope. So if we were to calculate the slope of this, it would be negative. So we're going to graph a negative slope, but this line is not curved. It's not changing. So this is going to be also be straight, but now it's going to be a constant value. Pretty simple. Now we're going to take the slope again. What's the slope of a flat line? Even if it's negative, it is. If this line is negative, it doesn't matter. It's still a flat line. It's unchanging line. So the slope is going to be 0 once again. Okay, we gave you the negative axis, but it's a trick question. Okay, it's 0. 0 acceleration. And our forces are the same. We have the same ground pushing down, gravity pushing down, ground pushing up. You add those together, they cancel out, and the net force is equal to 0. But you knew that already because our acceleration was 0. Pretty simple. So let's look at motion that accelerates.